Let's resume section 4. Previously, we discussed this problem using binomial means. How did he do that? Well, for individual Bernoulli trial, we get this, we proved it, and then apply the central limit theorem. So expected value stays as before, so same as P. And then the standard error is sigma over square root of n. So this over square root of n, simplify into this. And then we want this greater than 1/4. So here's a picture. Expected value is 210, so that's the center. And 1/4 or 0.25 is to the right, and then shading to the right. And look for the z-score associated to that, n minus center over SC. And then look up the table and do whatever. You'll be able to get whatever you want to. Get this one, the left-hand side shading from your z table, and subtract from 1. And that's how you get 0.188 something. And this was pretty good. And we could cross-check by direct binomial computation. And please note that 1/4 of 50 is 12.5. So 12 greater than 12.5, so we begin from 13. And we get that. But this is really a brutal computation. Only computers can handle this kind of thing. In the end, we get pretty good approximation. This versus that. Not much change. Now, this is for using binomial means. Can we do the same thing by binomial sum? What's the difference, by the way? From the central limit theorem, we get this for binomial average. And then what's the relationship between sum versus average? Add them all up, sum, and divide by n is the average. So in order to go back, we have to multiply by n. So that's what we did. Multiply by n, and simplify. That's how you get this formula. Expected value of np and standard error of square root of np1 minus p. That's for the binomial sum, or sampling distribution of sample sums. If you do that, well, you're using a bit different formula here. np, so 10 is the expected value for the sum. And then we're using different formula here, square root of np1 minus p. So you're going to get the standard error for the sum. And also, we are doing the sum, so it's not 1/4 you're looking for. The actual sum, that is 1/4 of 50, so bigger than 12.5. That's what you're looking for. So 12.5 or bigger, is that right-hand side, where the expected value is 10, 10. And then go ahead and do the same thing. Z-score, n minus center over SC, and then do your computation. 12.5 minus 10, n minus center, over this new standard error right here, and do your computation. And not coincidentally, you got the same thing as before, and we end up with the same answer as before. Work it out okay. But that's because this problem was exceptionally simple. Now let's go to the next problem. This time, things will not be very good. According to Federal Highway Administration's 2007 statistics, the percentage of female drivers is 50.2%. So, in binomial trial, or even before that in Bernoulli trial, the probability for success is 0.502, the proportion of female drivers. And then the number of repetition, n equals to 20. And then expected value of this binomial average. And that's going to be what? Just t, right? So this is what we're going to get. It's the same thing. And then what about the standard deviation of that? And this is going to be square root of p, 1 minus p over n. That's a formula, isn't it? So we have to do this computation, 0.502, 1 minus of that, and divide by number of repetition, that's 20. And then if you run your computation, it's going to be about this much, 0.11 something. Oop. So, did you get the normal approximation? The normal approximation centered at the expected value of 0.502 and the standard deviation of this. And then what is the question here? Use the binomial distribution to calculate the probability that less than half the selected drivers is female. Well, that's direct binomial computation, but we are in normal approximation here, so let's go to B first. The normal approximation to calculate the probability that less than half the drivers. Okay, so what do we want here? The probability that is that what we want? Or less than half? So less than 0.5. All right. Expected value, that's the center, and standard error. As a matter of fact, I should have said standard error, because this is central limit theorem, standard error, and then less than 0.5. So end 0.5, center 0.502. They are really, really close to each other. There is already one red flag, and the sample of 20 drivers, the repetition of 20, that's not large enough. Second red flag. And then there's still yet another red flag that I'm going to talk about a bit later. But in any case, let's just force into our conclusion. Keep doing that. Mean and the standard deviation, yeah, 0.502, same as before, and same computation, all right. Okay, and then we are looking for this quantity, and I'm using this Pn for normal approximation and for normal. If I draw a picture, what happens here, and this is already problematic because the center is 0.502 and this 0.5. They're so close, I cannot see the distinction in naked eye. Z computation is n minus center over SD. Let's see, do you see this? If I increase the font, do you see better? 0.5 minus 0.502 over the SE computation we did. We get negative 0.017 something. And if you look up this in normal table, you're going to get 0.4920 approximately speaking. And I get a little bit better figure by Mathematica, but still this is what I got from this normal approximation using this sampling distribution of sample mean. Will it work? Well, it won't. Let's go to binomial computation directly, and please recall that this is the probability mass function for binomial. And then calculate up to 9 people because, less than half. So half of 20 is 10, but less than 10, so I have to add up to 9 people. Does it make sense? Less than 10, that's equal to less than or equal to 9. There's nothing in between. We are talking about number of people. So add up to 9 and then do your computation. 20 choose k and then this power, that power, and 0.4048. That's what you're supposed to get. But the normal approximation gave us 0.49 something. This is terrible approximation. What went wrong? Well, number one, the sample size was too small. Just 20, not very good. And another, the expected value, 50.2%, 0.502, and then the problem, half the selected driver. They're too close. 0.502 and 0.5, they're too close. But that's not really the end of the problem here. The real deal is coming from 10 versus 9. So in binomial average problem, let's see, we did this, less than half of it, but that approximation turned out to be bad. Is there any way to improve it? You can do it through binomial sum. Sampling distribution of sample sums, and then the mean and standard deviation, or standard error, I should have said. Okay, and which probability do you want to estimate? This is a real key. Let's see, less than 10 people, because less than half of selected 20 drivers. So do I use normal approximation of x less than 10? But then again, that's the same as x less than or equal to 10, because normal is a continuous random variable. But then again, less than 10 people is the same as less than or equal to 9 people. So if I use the same logic, the normal approximation will become less than or equal to 9, which is the same as less than 9, which is less than 10 or less than 9. That's not the same. Less than or equal to 10 or less than or equal to 9. That's not the same either. So we have a conflict here. Which is right? How do we make it right? The best way is to settle it right in the middle. Do 9.5. You see, we have number of people. So number 1, number 2, number 3. So person number 9 and person number 10. And here I'm cutting through the person number 10. You can't do that. I'm cutting through person number 9. That's not right. You cannot cut a person into 2. You have to cut in between people at 9.5. If you do that, then the sampling distribution of sample sum method will yield pretty good approximation. So if you do 9.5, and then what is the expected value, by the way? And what's the expected value? Oh yeah, 10.04. So center is 10.04, 9.5 is there, and you can calculate n minus center over SE, do this z-score computation, yeah, like this. And then get the computation, look up the z-table up to the 2 decimal digits, and do your computation. You get an approximation that is actually pretty good. 0.4045, that's what I got. And compare that with the binomial computation that we did before. 0.4048, very close. Oh, by the way, this picture that I forgot to show you, this is a probability histogram that you get from binomial, but as you can see, that resembles normal very much. So the normal approximation is supposed to work, but it'll work only if you make appropriate adjustment to the endpoint like this, 9.5 like that. If you do it like that, then it'll work. Alright, so much for